Welcome to a video on the sum and difference identities for cosine, and the goals of the video are to use these identities to determine function values. So if we have the cosine of a sum or difference, here are the identities. The cosine of the quantity a plus b is equal to cosine a times cosine b minus sine a times sine b. And if we have a difference, it's equal to cosine a cosine b plus sine a sine b. Now instead of writing this as two different identities, sometimes it's written like this. And notice here we have a plus or minus sign, and over here we have a minus plus sign. So if we use the addition sign here, we would use the subtraction sign. And if we use the subtraction sign here, then we would use the addition sign here. Now I am including a slide that shows the proof of these identities. This proof is pretty straightforward if you set up this diagram using the instructions here and then follow the proof here on the left. So you may want to pause the video and take a look at this to see where these identities do come from. But let's go ahead and take a look at a couple problems using the identities. Here's a problem where we have sine A is 12/13 in the second quadrant and sine B is equal to 4/5 in the first quadrant. We want to find the cosine of the quantity a plus b. So let's go ahead and write out our identity. Notice if we have a sum, then we're going to use a difference of these two products. We are given sine A and sine B, but we still have to find cosine A and cosine B. So let's go ahead and sketch these angles in standard position. For angle A in the second quadrant, might look something like this, where our reference angle, or A prime, would be this angle here, and so the opposite over adjacent side would be 12/13. And this is a 5, 12, 13 right triangle, so this side would be labeled -5 since we are in the second quadrant. For angle B, in the first quadrant, has a sine of 4/5. So if we call angle B, this would be the opposite side, this would be the hypotenuse, and this is a 3, 4, 5 right triangle, so this side here would have length 3. So we'll use this information to complete our identity. So the cosine of angle A would be the cosine of this reference angle, which is adjacent over hypotenuse, or -5/13, times the cosine of angle B. Well, the cosine of angle B would be adjacent over hypotenuse, or 3/5, minus sine A times sine B. Well, sine A is given as 12/13, and sine B is given as 4/5. This product would be -15/65 plus -48/65, which gives us -63/65 for the cosine of angle A plus B. And this is what we were trying to find, so let's go ahead and state it one more time. Cosine of A plus B is equal to -63/65. Okay, let's go ahead and take a look at a couple more problems. Here we want to determine the exact value of cosine 15 degrees. Well, 15 degrees is not one of those nice reference angles, but we can use a sum or difference of two angles that would be reference angles to obtain an angle that would be equal to 15 degrees. So for example, if we use the reference angle of 45 degrees and then we subtracted the reference angle of 3 degrees, that would give us an angle of 15 degrees. So we can use angle A equal to 45 degrees and angle B equal to 30 degrees. So let's go ahead and set this up down here. We'll have the cosine of 45 degrees minus 3 degrees is equal to cosine A cosine B, cosine 45 degrees times cosine 30 degrees. Now we use the subtraction sign here, so we'll use an addition sign, and then it's going to be sine A times sine B, or the sine of 45 degrees times the sine of 30 degrees. Now we're going to fill in these values, find these products, and then find the sum. We'll go ahead and replace this now with 15 degrees. And I included the unit circle here. The cosine of 45 degrees, remember, is equal to the x-coordinate on the unit circle, so we have square root 2/2 times the cosine of 30 degrees. Well, here's 30 degrees, so our x-coordinate is square root 3/2 plus sine of 45 degrees, is also square root 2 over 2, and the sine of 30 would be equal to the y-coordinate, or 1/2. So here we have square root 6 over 4 plus square root 2 over 4. So now we know the cosine of 15 degrees is exactly equal to the square root of 6 plus the square root of 2 divided by 4. Now we can check this on our graphing calculators in decimal form. Let's go ahead and do that. First, let's check to make sure we're in degree mode. Press enter. Go back to the home screen, and we'll type in cosine 15 degrees, and then we'll compare this to what we found to be the exact value. And this verifies our work. Okay, here's another one, same idea, but now it's in radians. So sometimes it's difficult to determine which reference angles we can add and subtract to come up with this angle in radians. So let's go ahead and convert this to degrees first. This is equal to 105 degrees. So that should tell us if we use a 60-degree angle and we add a 45-degree angle, that would give us 105 degrees. But let's go ahead and be consistent and use radians. So 60 degrees is equal to pi over 3 radians, and 45 degrees is equal to pi over 4 radians. What this tells us is that cosine of 7 pi over 12 is equal to the cosine of pi over 3 plus pi over 4. And these are the angles we'll use in our identity. So again, we have cosine A times cosine B. Here we're using a sum, which means we'll use a difference in our identity. And then the sine of A times the sine of B. Cosine of pi over 3 radians, here's pi over 3 radians, so that's equal to the x-coordinate, or 1/2. The cosine of pi over 4 radians is equal to square root 2 over 2. The sine of pi over 3 radians would be square root 3 over 2. And the sine of pi over 4 radians would be square root 2 over 2. Notice we have a common denominator of 4. So what we have found is that the cosine of 7 pi over 12 radians is equal to, again, our denominator is 4, and our numerator would be square root 2 minus square root 6. Okay, I think I have one more question if we have time. Here we want to find the exact value of cosine 40 times cosine 50 minus sine 40 times sine 50. And what we should notice here is that it fits our identity when we're using a difference. So we're going to rewrite this in this form this time, and if we're using a subtraction sign here, we're going to find the sum of angle A and angle B, which are 40 degrees and 50 degrees. So this would be equal to the cosine of 40 degrees plus 50 degrees, which is equal to 90 degrees. Well, the cosine of 90 degrees, here we are on the unit circle. Remember, cosine is equal to x, so this is equal to 0. And that's all there is to this problem. Okay, I hope you found this video helpful. Thank you for watching and have a nice day. Welcome to a lesson on the sum and difference identities for tangent. And the goal of the video is to use the sum and difference identities to determine function values. So to find the tangent of a sum or difference, we will need to use one of these identities. If we have the tangent of the sum of two angles, it's equal to tangent A plus tangent B divided by 1 minus tangent A times tangent B. And if we have the difference of angle A and angle B, notice they look very similar, but the numerator is a difference and the denominator is a sum. And we can combine these two identities into one by using a plus or minus sign for the two angles, a plus or minus sign for the sum in the numerator, and a minus plus sign for the sum in the denominator. So if we use a plus sign here, we use a plus sign in the numerator and a minus sign in the denominator. And if we use a minus sign here, or a difference, we'll have a difference in the numerator and a sum in the denominator. I did include the proof of the tangent sum identity. We don't have a lot of time to go over it now, but just remember the first step is remembering that tangent theta is equal to sine theta divided by cosine theta, except now we're going to use the sum identities for sine and cosine. So you may want to pause the video and look over this, but it is pretty straightforward. Let's go ahead and take a look at some problems. If we want to determine the exact value of tangent negative 105 degrees, using reference angles we have to figure out how we can add or subtract them to obtain negative 105 degrees. And negative 105 degrees is equal to negative 60 degrees minus 45 degrees. So what that tells us is that we will use negative 60 for angle A and 45 for angle B, and we'll use the difference identity. So let's go ahead and set this up. So the tangent of negative 60 minus 45 degrees is equal to tangent A, or tangent negative 60 degrees. If we're using a subtraction sign, we'll use a subtraction sign here as well. Tangent B, or tangent 45 degrees. Now notice, since we're using the difference, angle B is positive 45 degrees. And we'll divide this by 1 plus tangent A, or negative 60 degrees, times tangent B, is 45 degrees. So now we'll go ahead and find these tangent values and then try to simplify this fraction. Tangent negative 60 degrees would be here. Remember, tangent theta is equal to y over x on the unit circle. Negative square root 3 over 2 divided by 1/2 would be the same as negative square root 3 minus tangent of 45 degrees. Here's 45 degrees, y over x, that would equal 1. Divided by 1 plus the product of tangent negative 60 degrees again, which we already found as negative square root 3, and the tangent of 45 degrees we already found as equal to 1. So this simplifies to negative square root 3 minus 1 over 1 minus square root 3. This is the tangent of negative 105 degrees. However, we're often asked to rationalize this. So let's go ahead and multiply the top and the bottom by the conjugate of the denominator, which would be 1 plus square root 3. Let's take this down here. Again, the tangent of negative 105 degrees is equal to this product. Let's start by multiplying the denominator together. These are conjugates, so we'll have 1, and then we'll have plus square root 3 minus square root 3, that's 0, and then negative square root 3 times positive square root 3 would be minus 3. In the numerator, we're going to have a negative square root 3 minus 3 minus 1, and then minus square root 3. Here we have negative 2 square root 3 minus 4 all over negative 2, and this simplifies. We have a common factor here of negative 2. This will simplify to positive square root 3, and negative 4 divided by negative 2 would be plus 2. And this is the value that we were looking for, the tangent of negative 105 degrees. So there's quite a bit of algebra once we find our function values here. So you got to be very careful and watch your signs and your products. Let's go ahead and try another. It's the same type of question, but now we have our angle in radians. So again, we'll convert this to degrees first. This comes out to 75 degrees. So we're going to use reference angles of 45 degrees and 30 degrees to obtain 75 degrees. But let's go ahead and use radians. So this would be pi over 4, and this would be pi over 6. Now we'll use a sum. So we'll have the tangent of A, or tangent pi over 4, plus tangent b, it's pi over 6, all over 1 minus tangent a, tangent b. Let's start evaluating this. Tangent of pi over 4 is equal to 1. Tangent of pi over 6, 1/2 divided by square root 3 over 2 will equal 1 over square root 3. Next, in the denominator we have 1 minus tangent of pi over 4, which is equal to 1. Tangent of pi over 6 was 1 over square root 3. Next thing we might want to do is clear these fractions. So let's multiply the top and the bottom by square root 3. So we'd have square root 3 plus 1 over square root 3 minus 1. Now again, this is the correct value, but we do need to rationalize our denominator. So let's go ahead and multiply the top and the bottom by the conjugate of the denominator again. So we'd have square root 3 plus 1. So again, what we have is the tangent of this sum, which originally was 5 pi over 12, is equal to, let's start with the denominator. Multiplying this out, we'll have 3 plus square root 3 minus square root 3, and then minus 1. In the numerator, we're going to have 3 plus square root 3 plus square root 3. That's 2 square root 3. And then 1 times 1 plus 1. So continuing to simplify, we have 2 in the denominator. We have 4 plus 2 square root 3. And again, this simplifies nicely. 4 divided by 2 is 2. 2 square root 3 divided by 2 is square root 3. So again, a lot of work algebraically, but we have found the exact value of tangent 5 pi divided by 12. And I think there's one more question. Use an identity to write tangent pi minus theta as a single function of theta. So let's see what happens when we apply this identity for tangent pi minus theta. Our numerator would be tangent pi minus tangent theta, and our denominator would be 1 plus tangent pi times tangent theta. Well, tangent pi on the unit circle would be here. Y over x would be 0 over negative 1, so that would be 0 minus tangent theta over 1 plus, again, tangent pi is 0, so 0 times tangent theta would still be 0. And it looks like it's going to equal negative tangent theta. Okay, that's all I have for this video. Thank you for watching and have a nice day. Here we want to apply the sum and difference identity and then simplify. So we have the sign of the quantity x plus pi over 2. So using our identity, we know that a is equal to x and b is equal to pi over 2. And since we have a sum of these two angles, this is the top operation here, we'll use the top operation here, which is plus. So wherever we see angle A, we'll replace it with x. So we'll have sine x here and cosine x here. And we'll substitute pi over 2 for b. So I'll have cosine pi over 2 here and sine pi over 2 here. So we'll have the sine of x times cosine pi over 2 plus cosine x times the sine of pi over 2. And now we can evaluate cosine pi over 2 and sine pi over 2. Well, cosine pi over 2 is equal to 0, and sine pi over 2 is equal to 1. So this is 0, and this is going to be cosine x. Sine of the quantity x plus pi over 2 is equal to cosine x. Let's go ahead and try a second example. Here we have the same type of problem, but now we're going to have to apply both the difference identity for sine and sum identity for cosine. So in both cases, notice that A is the first angle. So we'll have pi over 6 here, here, and here. And we'll have pi over 3 here and here. And then the second angle here is B in both cases. So for the difference identity for sine, this is y, so we'll have a y here and a y here. And then for the sum identity for cosine, b is equal to y, so we'll have y here and y here. And since we have a minus sign here, notice this is the bottom operation, we'll have a minus sign here. And then for cosine, since we have an addition sign here, which is the top operation, we'll have a minus sign here. So let's go ahead and write all this out. We're going to have the sine of pi over 6 times the cosine of y minus cosine pi over 6 times the sine of y plus, now we'll apply the cosine identity. So we'll have cosine pi over 3 times cosine y. And since we're using the plus sign here, we'll use the minus sign. And then we'll have sine pi over 3 times sine of y. Notice here we have pi over 6 and pi over 3, so let's go ahead and sketch a 30, 60, 90 reference triangle. And now we'll evaluate sine pi over 6, cosine pi over 6, cosine pi over 3, and sine pi over 3. So the sine of pi over 6 for 30 degrees will be 1/2. Cosine of pi over 6 is going to be square root 3 over 2. Cosine pi over 3 is going to be 1/2. And the sine of pi over 3 is going to be equal to square root 3 over 2. And now we just need to combine like terms. Notice here we have 1/2 cosine y plus 1/2 cosine y. That simplifies nicely to cosine y. Then here we have negative square root 3 over 2 sine y minus negative square root 3 over 2 sine y. So you can think of this as negative 1/2 square root 3 over 2 and another negative 1/2 square root 3 over 2. So that's going to be negative 2 square roots of 3 over 2, or just negative square root 3 times sine y. And now we've applied the identities and simplified. In this example, we want to simplify and evaluate using the sum and difference trig identities listed here below in red. So the first step is to recognize which identity we'll be applying. Notice that we have the sine of pi over 2 times the cosine of pi over 6. Well, the sum identity for cosine has cosine A, cosine B, so that's not going to work. So we'll be applying the sum and difference identity for the sine function. But we'll be applying this from right to left, meaning we're given this form of the identity, and we're going to rewrite it as the sine of one angle. So let's go ahead and write this. So here we have the sine of angle A times the cosine of angle B. Notice how we have a minus sign, and then we have cosine A times sine B. So A is equal to pi over 2, and B is equal to pi over 6. And because we're using the subtraction sign here, we'll also use the subtraction sign here, so we'll have the sine of A minus B. And since A is pi over 2 and B is pi over 6, this is equal to the sine of pi over 2 minus pi over 6. So now if we obtain a common denominator by multiplying both the numerator and denominator by 3, this is equal to the sine of 3 pi over 6 minus 1 pi over 6, which is equal to 2 pi over 6, which is equal to the sine of pi over 3. Well, pi over 3 is one of those nice reference angles. That's equal to 60 degrees. So if we sketch a 30, 60, 90 triangle, hopefully you're familiar with the relationship among the three sides. We can label the short leg 1, the hypotenuse 2, and the longer leg square root 3. So the sine of pi over 3 radians, or 60 degrees, would be equal to square root 3 over 2. So this expression simplifies to the sine of pi over 3, which is equal to the square root of 3 over 2. Let's take a look at another example. Here we have the same type of problem, but it's much more obvious we're going to be using the sum and difference identity for the tangent function. So the main things to identify here are angle A, angle B, and then whether we have a sum or difference here and a sum or difference here. That'll tell us whether we're going to add or subtract angles A and B. So angle A is 12 degrees, angle B is 18 degrees, and then we have a plus sign in the numerator and a subtraction sign in the denominator. So if we use a plus sign here, notice how we're using the top operation, and we're also using the top operation here. Therefore, we'll be using the top operation to combine angles A and B. So this is equal to the tangent of 12 degrees plus 18 degrees, which is equal to the tangent of 30 degrees. So we can use that 30, 60, 90 reference triangle again to determine this function value. The tangent of 30 degrees is going to be equal to the ratio of the opposite side to the adjacent side. So we'll have 1 to square root 3. We'll go ahead and rationalize this. So this simplifies to square root 3 over 3. We'll take a look at some additional simplifying examples in the next video where we use the identities in the opposite direction. We're given sine A equals -2/5 and cosine B equals 1/3, with angle A and B both in the fourth quadrant or in the open interval from 3 pi over 2 to 2 pi. We want to determine sine of the quantity A plus B as well as cosine of the quantity A minus B. So we'll be applying the sum and difference identities provided here below. But before we apply these identities, notice how even though we're given sine A and cosine B, we also must determine cosine A and sine B. So we'll determine these missing trig function values using the reference triangles provided here on the right. Where to model angle A, we'll use alpha as the reference angle, and to model angle B, we'll use beta as the reference angle. And since we're given that sine A equals -2/5, and we know sine theta is equal to y over r, where sine theta is equal to the ratio of the opposite side to the hypotenuse, where r, the hypotenuse, is always positive, we would label the opposite side at -2 and the hypotenuse, or r, +5. And now we can find x, or this adjacent side, using the Pythagorean theorem, where x squared plus y squared, or -2 squared, equals r squared, or 5 squared. So we'd have x squared plus 4 equals 25. Subtracting 4 on both sides, we have x squared equals 21. Solving for x, we would take the square root of both sides. So we have x equals plus or minus the square root of 21. But we know we're in the fourth quadrant where x is positive, so we'll label the adjacent side positive square root 21. Which means now we know cosine A is equal to x over r, or the ratio of the adjacent side to the hypotenuse, which is square root 21 divided by 5. And now we'll construct the reference triangle for angle B. And we know that cosine B equals 1/3, and cosine theta is equal to x divided by r, or the ratio of the adjacent side to the hypotenuse. So we would label this leg of the reference triangle 1, and r, the hypotenuse, 3. So to find the length of the opposite side, or y, again we'll use the Pythagorean theorem, where x squared, or 1 squared, plus y squared equals r squared, or 3 squared. So we have 1 plus y squared equals 9. Subtracting 1 on both sides, we have y squared equals 8. Taking the square root of both sides, we have y equals plus or minus the square root of 8, but this does simplify since 8 is equal to 4 times 2, and the square root of 4 is 2. We have y equals plus or minus 2 square root 2. But again, because we're in the fourth quadrant where y is negative, y is equal to negative 2 square root 2, which means sine b is equal to negative 2 square root 2 divided by 3. Now we have all the trig function values that we need, and we can now apply the sum of difference identities. So sine of the quantity a plus b is equal to sine a times cosine b plus cosine a times sine b. So again, we have sine a times cosine b plus cosine a times sine b. So subbing in the values, sine a is equal to negative 2/5. Cosine b is equal to positive 1/3. Cosine a is equal to square root 21 divided by 5. And sine b is equal to negative 2 square roots of 2 divided by 3. Notice how we do have a common denominator of 15. The numerator would be, here we have negative 2 times 1, that's negative 2. Here we'll have plus and negative, or just minus, and then we'd have 2 square root of 21 times 2 is 42. And the square root of 42 does not simplify, since the prime factorization of 42 is 2 times 3 times 7. So this would be the exact value of sine of the quantity a plus b. Now let's look at the second part of this question. Notice that cosine of the quantity a minus b is going to be equal to cosine a times cosine b plus sine a times sine b. Notice how because we have a difference, we'll be using a sum when we apply the identity. So again, we have cosine a times cosine b plus sine a times sine b. So again, subbing in the trig function values, cosine a is equal to the square root of 21 divided by 5. Cosine b is equal to 1/3. Sine a is equal to negative 2/5. And sine b is equal to negative 2 square root 2 divided by 3. Once again, notice how we do have a common denominator of 15. Here we have square root 21 times 1, of course that's square root 21, plus negative 2 times negative 2 square root 2 would be positive 4 square root 2. So this would be the exact value of cosine of the quantity a minus b. I hope you found this helpful.
Angle A is in quadrant 2 and angle B is in quadrant 4. If sine A equals 2/3 and sine B equals negative 4/5, determine sine of the quantity A plus B and sine of the quantity A minus B. Looking at the sum of difference identities, notice how we are going to have to find the cosine function values for angle A and B, and therefore let's begin by determining the reference triangles for angle A and angle B. We know angle A terminates in the second quadrant. Let's just say this is the terminal side of angle A, and therefore the reference angle is going to be this angle here. We'll call it A sub r. The reference triangle is this right triangle here. And because we know the sine function value is 2/3, we can label the opposite side positive 2 and the hypotenuse positive 3. And now we can use the Pythagorean theorem to determine the length of this leg, which because we are in the second quadrant is going to be negative. Let's go ahead and label this leg x and then find x using the Pythagorean theorem, which gives us x squared plus 2 squared equals 3 squared. Simplifying, we have x squared plus 4 equals 9. Subtracting 4 on both sides gives us x squared equals 5. And now we take the square root of both sides of the equation, which gives us x equals plus or minus the square root of 5. But again, because we're in the second quadrant, we know x is negative, and therefore we label the leg negative square root 5. We also know angle B is in quadrant 4. Let's assume this is the terminal side of angle B in quadrant 4. The reference angle is going to be this angle here. We'll call it B sub r. And the reference triangle is this right triangle here. Because the sine function value is negative 4/5, and we know the hypotenuse is always positive, we label the opposite side negative 4 and the hypotenuse 5. We also know this leg would be negative because we're in quadrant 4 where y is negative. And now we need to find this leg here, which we'll label x. Using the Pythagorean theorem, we have x squared plus the square of negative 4 equals the square of 5, giving us x squared plus 16 equals 25. Subtracting 16 on both sides gives us x squared equals 9. And now we square root both sides of the equation, which gives us x equals plus or minus 3. But because we are in quadrant 4 where x is positive, this leg is labeled positive 3. Now we have all the information we need to find sine of the quantity a plus b and sine of the quantity a minus b. Using the identities, we have sine of the quantity a plus b equals sine a times cosine b plus cosine a times sine b. Let's go ahead and list out these 4 trig function values here below. Well, we know that sine a is 2/3. Cosine a is equal to the ratio of the adjacent side to the hypotenuse, which is negative square root 5 divided by 3. And then we need to find sine b is given as negative 4/5. And cosine b is equal to the ratio of the adjacent side to the hypotenuse, which using this reference triangle is 3/5. And therefore sine of the quantity a plus b is equal to sine a, which is 2/3, times cosine b, which is 3/5, plus cosine a, which is negative square root 5, divided by 3, times sine b, which is negative 4/5. Simplifying, we have 6/15, and then plus a negative times a negative is positive, and therefore this is plus 4 square root 5/15, giving us the quantity 6 plus 4 square root 5, all divided by 15. And now we need to find sine of the quantity a minus b, which is equal to sine a times cosine b minus cosine a times sine b. Well, notice how this expression is the same as this expression here, except instead of a sum, we have a difference. And therefore this difference is going to be equal to 6/15 minus 4 square root 5/15, or the quantity 6 minus 4 square root 5, all divided by 15. I hope you found this helpful.